I am Hanson Sue, and the date is April 24th. And can you introduce yourself?
I'm Jakob Uszkoreit. Today I'm the CEO of Inceptive. And before that, I'm one of the co-authors of Attention is All You Need and a bunch of other scientific publications.
Thank you. So can you tell us how you got into the field of artificial intelligence?
In many ways, that was actually something that I guess as a problem runs in the family. So my dad is a computational linguist, used to teach that and computer science in Germany in universities. Before that, worked at SRI in Menlo Park and spent quite some time in Stanford. And so in a certain sense, it's something that started to enter my life over dinner conversations when I was a young child. And then later on, I started going to university in the early O's back in Germany again. Actually, to a certain extent, tried to avoid artificial intelligence / machine learning, certainly when it comes to applications around language, in order to at least stray a little bit from the family business. And then in 2006, I stumbled upon a Google internship not too far from here. And they offered me a few different research projects that I could join. And machine translation by far had the most interesting large-scale machine learning problems. And so with some chagrin, I bit the bullet and actually did end up in the family business of sorts.
Interesting. So when your father was working in computational linguistics, so what were the techniques then, and how would you contrast, the techniques that he was using versus the techniques that you were using?
So in those days, in computational linguistics, the techniques were they were becoming more data-driven. There was more and more machine learning being applied, at least in certain specific parts of larger systems. But they were still certainly heavily informed by and oftentimes really driven by linguistic insights in a certain sense, in the broadest sense, theory of language or theories of language that were used as, again, in the at least underpinnings in how those systems were designed, but oftentimes really were used as the backbone of how they actually operated. In stark contrast, what we started doing already in 2006 and 2004, 2005, 2006 at places like Google Translate was much less informed by basically our conceptualized understanding of language, or a conceptualized approximation of an understanding of language, and was trying to be more black box, yet at the same time often still constrained by say combinatorial optimization algorithms that made strong assumptions about how oftentimes the outputs of such systems, such as Google Translate, would be assembled as functions of the input. And so, for example, at the time, the leading approach was statistical phrase-based machine translation, where you make the assumption that you can chop the input sentence or input string into phrases, each of which have a small number of candidate translations. And then what you're actually doing is, within a certain search cone, so to speak, you're allowing yourself to reorder those, not embracing the full combinatorial explosion of all possible reorderings, but you're allowing a limited amount of reordering and choice among those phrases. But that means you're still making a strong assumption when it comes to basically how the equivalence can be expressed between two sentences in two different languages. What happened then with basically the renaissance or resurgence of deep learning and applying that increasingly to language was really to, in many ways, reduce the assumptions or limit the assumptions that had to be made about any such correspondences to an absolute minimum, and treat it really as a black box problem.
Right. So then the time that you were describing your father working on it, what years were those?
I mean, those were basically 80s, 90s, and then the O's. And in the O's, I guess, was when really the transition happened from systems that were largely rule-based, largely based on, again, conceptualized theories, if you wish, understandings of phenomena like language, towards things that were where at least you had larger numbers of parameters that were estimated using machine learning methods, and where the constraints were still informed in a certain sense by linguistic understanding, but not anymore basically forming the actual backbone of those systems. But yeah, those were basically those 3 decades where that shift happened, or over the course of which that shift also happened.
So there's been, over the 3 decades, there's been an increasing progression towards removing linguistic knowledge from the machine learning systems.
Removing it from the machine learning systems, or maybe from the perspective of some of the practitioners at the time, moving it from the actual implementation and the algorithms into constraints on statistical models that were then used to capture those phenomena. But I would say also, in a certain sense, weakened, right? So making fewer, or basing it less on ultimately theory, if you wish. Yeah, that's right.
Okay. So I read that like around 2012, so when you first started in 2006,
Yep.
were you immediately put on Google Translate? Or
Yeah, that's right.
Okay.
Yeah.
And then by 2012, what were you working on at that point?
By 2012, I had actually recently transitioned out of Google Translate and into a new team that at the time internally was called Aqua, that we had dubbed Aqua. Didn't stand for anything in particular, but what it was really is the language understanding team of the product that later became known as the Google Assistant. It wasn't called that yet, neither internally nor externally, but had basically started working on systems that effectively, in the broadest sense, semantically parsing queries, would enable Google search, especially on mobile, especially in certain interfaces, to use if you wish, deeper understanding and more explicit formalization of an understanding of a query that may have been formulated more in natural language than in Googleese, as we would call, in order to immediately give answers or execute actions that the user may have desired.
Mm-hmm. And was that motivated by competition?
That's right. That's right. So basically, that was motivated ultimately by Apple's Siri, and the concerns or the concern that Siri could change the way people expect to search and obtain answers, but also execute actions, in particular through when dealing with their mobile devices.
Mm-hmm. And what were the limits of the technology at the time?
I would say, compared to what we're able to do today, it was incredibly limited. And one of the issues was that the statistical methods, so we were still applying methods that were, if you squinted, very reminiscent of statistical machine translation systems. And what that implied was that we actually had to fabricate training data that was remarkably similar, all the way to, say, what type of question was being asked or what precise action was requested of a device, say to schedule a timer or an alarm or some such. And we had to gather quite a bit of training data from humans, or fabricate training data using humans, that was remarkably similar to what we would actually expect to see in the query stream. And we were only to an extremely limited extent able to use very large amounts of language in different domains and of different types in improving our understanding of queries and from such a distribution. And so really we couldn't really bring to bear, say, the majority of the web or so. right? It basically was all purpose-built, manufactured. In fact, we used at the time large numbers of what I guess we would now, or one would maybe call gig workers, in order to fabricate that training data, because there basically was no such data. There was no data in existence that was sufficiently similar to what we expected that query stream to look like.
And so can you describe to someone of a high school level what is an RNN and an LSTM, and explain the full acronym?
Okay, so RNNs are recurrent neural networks. LSTMs are long short-term memory recurrent neural networks. Basically, what they do is they evolve in steps that are taken in a recurrent fashion. We'll get to that in a second. They evolve a vector space representation of something that is seen as a sequence of elements. And so let's say in language, the sequence of elements could be sequences of words. Each of those words is represented by a vector. At first, it could be something like an indicator vector that, for any word in your dictionary has exactly one dimension, and there that vector has the value 1 and has zeros elsewhere. But then that vector is mapped through a lookup table, if you wish, onto some vector in some higher dimensional space. So now we have a sequence not of words anymore, but of vectors in some higher dimensional space of real numbers. And this RNN now evolves a representation of that entire sequence, or basically series of prefixes of that entire sequence, by mapping the next, or the current vector that it is, the current word vector that it is consuming, through some mathematical mapping, and then merging that into an existing state vector. And so you have some state vector that starts with some initialization, initial value, and now in every step you basically take in a new word vector. In the case of a sequence of words, you send that through some mapping, and then either in the course of doing that mapping or with a separate mapping, you now merge that into, basically added with some weighting, into your current state. And then you proceed to the next word vector and again add that into your current state, and you also at every given step potentially transform your state in a way that is independent of the next word vector. Now in LSTMs, what you do is LSTMs are a special version of all of these mappings, basically the mappings that control how you integrate the next word vector, how you integrate the previous state vector, and with some additional bells and whistles around the ability to basically, in a certain sense, forget your previous state as a function of the new word, to retain a certain amount of the previous state, to ignore the current word as a function of your state and as a function of the new word, and so on and so forth. And so basically it allows you it allows the model, how should I say, a sharp control to a certain extent, to learn to control sharply how much of these various state or new word vectors to use in the computation of the subsequent state vector.
Okay.
If that makes sense.
I'm not sure I fully got that, but that's okay. We'll move on.
Okay.
So talk about what led to the invention of the transformer and what was the key insight.
Okay, so ultimately, the situation we found ourselves in at the time was that these recurrent neural networks, that again, coming back, basically had to evolve some kind of state vector, some kind of state representation over the course of some sequence of vectors, such as vectors representing words, that when training those models on very large amounts of data, as you would find in some problems, say in Google search, you would actually never reach the performance of much simpler neural network models trained on the same data. And the reason was that these much simpler neural networks trained orders of magnitude faster. And so even though they were much less expressive, say, for example, simplistic feed-forward neural networks, multi-layer perceptrons, for instance, that you could easily show were not as expressive as RNNs or LSTMs, because, for example, they couldn't actually iterate through these sequences. They had to chop those sequences into n-grams and then map those onto vectors and just add those, basically forgetting about the global ordering of them and so on and so forth. They couldn't be that expressive, but because they were training so much faster, you could actually, they would actually see much more, orders of magnitude, more training data in any given amount of time than, say, an RNN or an LSTM, and would, as a result, still perform better in practice than these much more expressive models that we knew could actually handle language in a much more holistic manner, or phenomena in language such as long-distance dependencies in a much more holistic and much more appropriate manner. And so at the end of the day, and this wasn't true for all problems at the time, this was really pronounced only in cases where you really were able to generate massive amounts of training data, such as for dealing with queries in the regular web search query stream, of the regular web search query stream at Google. And it also, it basically made it clear that if we could find a way of making such feed-forward models train much faster on whatever hardware we had, we could potentially actually get the best of both worlds, right? If we could make them, I think that came out wrong. I think if we found a way of making these feed-forward models more expressive, akin to RNNs or LSTMs, yet somehow retain their fast training speed, that we would actually get the best of both worlds, basically have models that could really be expressive enough to capture language as a phenomenon fully or holistically, while also benefiting from these vast amounts of training data that we were able to manufacture. And one of the fundamental insights from a linguistic perspective, or just from a statistical perspective, this doesn't just apply to language, this applies to many different signal types. One could argue all signal types that we can make any sense of, in fact. One maybe philosophical insight here is that this must be possible by exploiting the fact that there is a hierarchical nature to at least our understanding of pretty much every stimulus that we get. Meaning, we basically, in language, for example, right, if you, in grade school or later high school, you parse sentences, right? What you're really doing is you're expressing the fact that there is hierarchical substructure where you have individual phrases that basically, where you can, in a certain sense, arrive at some understanding of, in quotes, most of their meaning just looking at that phrase, and then maybe you have another phrase in a sentence where the same is true, and then the third one, and now in another pass, you don't actually need to go through every single word anymore in sequence. You can aggregate these, what you've basically already in isolation determined as the meaning of these individual phrases, and put those together to the meaning of a bigger phrase, and so on and so forth. Now, why is that insight interesting? It's interesting because the hardware that we had at the time is actually still remarkably similar to the accelerator hardware that's being used in deep learning today. It excels at parallel processing. And so if you're able to identify what are some of these chunks that you can, in isolation, make some sense of already without looking at everything, then you've just enabled parallel processing. So basically you've said, okay, fine, then we look at this phrase in isolation, get to some extent an understanding of what they mean, some vector space representation of what they mean. And then in the next step, we'd only need to actually aggregate those basically representations, and so on and so forth. And that's in direct contrast to what RNNs do, right? Because they walk through the entire signal step by step, one after the other, and they have to do that in order to then arrive at some state representation in the very end after having run through that entire signal. And so basically, what motivated these then self-attentional models was this insight that by basically paying what looks like a performance penalty initially, namely by having every piece of the signal interact, but in a very shallow way, with every other piece of the signal, that doing that would enable it to actually, in a certain sense, build soft tree structures over your entire signal that would then ultimately exploit the ability of these accelerators to do parallel computing as opposed to sequential computing. So you basically parallel compute the interactions between all pieces of the signal, or every piece of the signal, with every other piece, pairwise, if you wish, and then you would just repeat that step. And it turns out that you don't need to repeat that nearly as many times as the signal is long. And that is ultimately what makes this type of parallel processing way faster on hardware that is very good at performing this large number of but more simple kind of pairwise comparisons, in contrast to a sequence length many harder operations, if you wish, that then tried to basically keep that global state up to date at every given step.
Okay, so it sounds like in computational terms, you're going from a linear algorithm to something that's
Logarithmic.
Logarithm. Okay.
Exactly. That's exactly right.
Okay.
But you can't directly. You don't know the tree, and so as a result, you can't directly. And this is what if we knew the tree, or if there was really truly a tree. I don't believe there truly is a tree, right? Because it's only approximately correct that these signals are tree structured or truly hierarchical. But if we knew a tree, and if it existed, we would just draw the tree, and then we would basically just aggregate the individual representations along that tree, and then we would actually end up at something that is logarithmic if we process it in parallel, right? Because we only need logarithmic many steps in terms of tree depth in order to actually process the signal of a given length. We don't know the tree. And so as a result, how do you approximate the tree? You don't know which basically branches. Let's assume it's a binary tree, so at every given level, two things are paired up. We don't know what that tree looks like. Okay, seems silly, but why don't we iterate over all possible pairings? And now this at first looks counterintuitive from a computational efficiency perspective, but if you make that very simple, and in case of these self-attentional models, what usually this operation looks like is just an inner product. If you make that really simple, then you can do many of these inner products in parallel. There's no sequential dependency whatsoever. That's what these accelerators love. And then effectively have iterated over all possible branchings at that level. And then you take another step and you iterate over all possible branchings again and again. And so basically, if you happen to have hardware that looks like these accelerators, like GPUs, TPUs, et cetera, then that is a much better allocation of compute than requiring it to be more complex, basically matrix multiplication steps, a few or so per step, but then times the length of the system overall, length of the signal overall.
I see. So what is self-attention and how does it work?
Self-attention is a way of imbuing feed-forward models that don't require recurrent steps along the length of a signal, with a effectively global receptive field, with a way of looking at or of considering all possible pieces of an input signal at any given moment, at any given step. And so the way in the transformer and in its predecessors, decomposable attention model, etc., that we published before, the way that worked was by effectively doing pairwise comparisons, exactly like I just explained, right? So instead of aggregating a certain kind of state by doing a set of matrix multiplications for each new element and doing that in order, you now basically process, you compare every single pair of representations. That gives you a weighting of, for any given element, of all other elements. So if we want to go into more detail here, what you do is these pairwise comparisons give you scalars for each pair of representations. In fact, maybe even for every given position, they give you a scalar for every other position. Now you could normalize those into something that sums up to 1. You can call that a distribution over all other positions. And now you can just add those up, weighted by exactly that distribution. And so in a certain sense, you can conceptualize this as for every given position in your signal, let's say it's a word, you're getting at every given step a weighting of all other words. And you could say, even though that's taking it a little bit too far, but maybe slightly oversimplifying, you could say that tells you how important at this moment each of these other words is for determining the meaning of that word. Then you basically aggregate those in an operation that is totally simplistic. You just add them up, and then you send that through one basically feed forward through a small MLP, but that small MLP now operates only on this aggregation. So you basically...
What's an MLP?
Multi-layer perceptron.
Okay.
So a very simple feed-forward network. Again, no recurrence, no iterative process. Basically, you have this very simplistic addition that is, in a certain sense, independent of. It's not truly independent of the length of the signal, right? But it's very, very simple. You can apply it to very large signals, and then you just end up with one vector again, and that you send through this simple multi-layer perceptron. In fact, usually a pretty small one. And you do that again in parallel, independently, for each of your positions, for each of your words. So in every step, what you do is for each word, you attend to every other word, meaning you get a distribution over all the other words. Weighted by that distribution, you sum them all up. So say if you want something that looks like a tree, then your distribution is very peaked only on one other word, and it's almost 0 for all the others, right? And so that now means you're just getting the vector from just that one other word. You add it to your own. You send that through your feed-forward network, through your multi-layer perceptron, and that then forms the representation for the word in question that we're talking about in the next layer. And that's the process that gets repeated layer after layer. But in every layer, you do it not just for one word, but for all of them in parallel. But they're all independent, right? Because you don't need to know the new representation of any other word in order to compute your new representation. And that is what, again, shapes the workload into something that is much more manageable and much more efficient, ultimately, on today's very parallel accelerator hardware.
Okay. Could you maybe define, because I'm not sure the audience understands the difference, define recurrent and feed forward?
Okay. So basically, a recurrent neural network processes a given signal in a fashion that is iterative. So it steps through every element of that signal, and if that signal is, say, a sentence, as it would be commonly represented, then for every word in it, every token, you have one vector, and you now basically process the first vector, and then you get a state. Then you somehow process the next word vector and your state, and you integrate them into some new state, and you keep doing that. Problem with that is, it takes you, at the very least, as many steps as your sentence is long. A feed-forward neural network, or MLP, basically takes some fixed length input and sends that through a series of such transformations, the same that you apply as you recur through your signal in a recurrent neural network, very similar, but only in a fashion that only applies to one fixed length, and hence also has a fixed number of operations. Now that means if you want to process signals of variable size with something that is feed forward, you traditionally had to somehow aggregate that into something of fixed size. And the way that would oftentimes happen is by just saying, okay, if we take our sentence with a word vector per word, and now we have moving windows of, say, 3 words or so, and we basically, for each of the 3 words under this moving window, we map them onto one vector, and then we just add them all. Now we have one vector, and that we can send through a feed-forward structure, network structure. if you wish. But now you've lost all ordering information, right? And so what self-attention, coming back to what we talked about before, does is it gives you a way of processing something of variable size, despite the fact that what you're doing is you're just applying feed-forward elements. There's an important detail which I didn't mention so far, which is that in the way I just described self-attention, you would have still forgotten the ordering. In order to retain the ordering, you need to basically infuse each word vector with some representation of where the word was in the signal, in the sentence. But once you have that, you can actually retain the ordering in a way that is not recurrent, that doesn't require you to do a number of steps, that is a function of the length of your signal.
Okay. So why did you call it a transformer, and who came up with the name?
So why do we call it a transformer? Ultimately, it makes a lot of sense if you think about this kind of holistic transformation of the entirety of the signal in every step, right? In contrast to recurrent neural networks that evolve a representation over, as they recur, as they iterate over a signal, right? This thing basically has some representation of the whole thing and transforms it in whole. You could argue it is that difference isn't, maybe that what recurrent neural networks do also is a transformation. It certainly is, but up to that point, nobody else had used the name. It seemed to be pretty fitting. I had some transformer toys when I was a kid that I really liked. I came up with the name, but it was, there was some tongue-in-cheek swagger, if you wish, in the choice of the name too. So it was, we I would say among us, still even among us somewhat secretly, but we did have high hopes for this to maybe also be transformational. But
interesting. Can you talk about coming to assemble the team that came together on this paper?
So the team came together in a bunch of different waves, if you wish, and those waves were by no means planned or orchestrated. What happened was that Ilya Polosuchin, who was running a team, a part of my team at the time, in Google Research, had decided to leave the company. And so he had several months during which, as far as I recall, he was waiting for his co-founder to be able to leave behind what he was doing at the moment, although I'm not 100% certain about that anymore. But basically there were a few months that he was still going to spend at Google, but he knew, and we knew, that he was going to leave after that. And so his appetite for risk skyrocketed, effectively, compared to what he was doing before. Before, he was managing a larger sub-team of mine, and they had some pretty clear engagements with search, with product teams. And so once his transition out began, he basically was, with a much increased appetite for risk, looking for something crazy to do. And this is in the context of a group that had just published a paper on a model called decomposable attention model that was also a fully self-attentional model. The first one, we believe, of that kind, and we were playing with self-attention mechanisms in a bunch of different applications and in a bunch of different shapes and forms.
Was that the first publication of attention at all?
No, so attention actually, not in the self-attention manner, was applied in sequence-to-sequence or seek-to-seek RNN LSTM models routinely at the time.
Okay.
So you would basically, the mechanism that I described, where for any given word you get a distribution over the other words, you would do that, but for every given word you would get a distribution over, say, for every given output word in the translation system, you would get a distribution over input words. And so that mechanism, attending from one signal into another, was being used routinely, was part of the state-of-the-art in machine translation at the time. There was another group in Edinburgh, actually, that was also looking at a self-attention mechanism in order to improve RNNs. So there basically, as an RNN would generate output, they would attend to the previously generated output. But aside from that work, we believe we were actually the first to publish back in 2016 on self-attention. And now that publication actually, we were working on that already in 2015, and before, it just took us a while to get around to writing up a short paper for EMNLP and publish that there. But basically that was the context of the group, so we had already applied mechanisms like that, although implemented in a much less scalable way, to be clear, to a bunch of different types of signals, including language, but on much smaller tasks than large-scale machine translation. And I had high hopes for basically replacing recurrent neural networks wholesale in seek-to-seek style models that were applied to, say, all sorts of things from machine translation to Gmail autocomplete and lots of other problems at the time. And so, Ilya said, why not? Sounds crazy, but that could actually work. He was also quite hopeful that there would be practical applications also for his soon-to-be former team, because it could potentially speed up question answering models that they had been working on in Google search, where latency requirements were actually very, very tight. And very quickly, Ashish Vaswani, who was at Brainin at the time, was also looking for something new to do. He had worked on a few different projects, but nothing really with the potential, at least, that he was looking for. He was also looking for something new. I talked to Ashish around the time that he started a whole bunch, and so they started hacking away on this, and we wrote up some initial design doc that basically just said we're going to apply this to all sorts of different problems, iterative self-attention for all sorts of different problems, including machine translation. And then we had a meme there of a bunch of transformers zapping lasers, and they got going on actually trying it out. And actually, and now I don't remember the exact sequence of events, at some point in time, Nikki Parmar, who was also on my team at the time, joined forces and started running experiments, and we saw first signs of life. But also saw those two plateau after some time, and that's not uncommon in these kinds of efforts, because it turns out that even if your intuitive or conceptual idea for a mechanism has lots of promise or holds lots of promise, you really need to get all the implementation right. You need to really optimize it, because everything has to do with computational efficiency. And we were building, basically I shouldn't say we, actually it was really Ashish and Ilya and Nikki, they were building this code base from scratch as a new research code base. They simply hadn't had time to implement all the bells and whistles of what then was basically super fast moving modern day deep learning. And around that time, when we joined through happenstance ultimately, some folks in the Brain team, Noam Shazir, Lukasz Kaiser, and Aidan Gomez, saw what we were doing there and decided to experiment with the self-attention mechanism in a code base that they had been building at the time, actually in order to build convolutional seek-to-seek models. So a different attempt of moving away from recurrent models in seek-to-seek, but based on convolutions, and they then added the self-attention mechanism to it, and it really improved their results, and they had a code base that actually had all the bells and whistles. And then came a crazy period of time when basically Noam, Lukasz, and Aidan ripped out what they had put in, the other mechanisms that they had put in before. And in the end, we're left with something that was purely self-attentional. It looked a lot like the architecture that Ashish had, and Ilya had left the company by now, but that Ashish had put together, or that Ashish had at the time. But it was now implemented in this other framework with all the black magic tricks, and in a way that really, Noam, who's one of the most legendary deep learning magicians there are, right? He then ultimately also implemented that mechanism in a very, very efficient way. And so what started then was actually the end of that plateau, and that turned into just rapid improvements in performance of these models for basically almost every day for months. And yeah, it was just an incredible, incredible ride.
So there's a very interesting thing that you just talked about, which is that the insight that was discovered was that by taking out these things, these quote bells and whistles that you mentioned.
Well, the bells and whistles were important in terms of training tricks, et cetera, et cetera. But it was other mechanisms, convolutional mechanisms, et cetera, et cetera. Those were the ones that we removed. And that's what actually, reduced it back to this very pure self-attentional architecture that then also worked really well once in that other code base that had all the tricks of the trade, if that makes sense. So we took out other architectures, but it now was implemented very efficiently by Noam in this code base that had all the tricks of the trade. So basically the differentiation here is the tricks of the trade, the deep learning black magic, that was crucial to have. But what they had before was something that had some convolutions and some other stuff, and and then they had added the self-attention mechanism on top of that. And what they then did was remove all the other stuff they had before they added self-attention, being left with just self-attention, but now newly implemented super efficiently in this code base that had all the tricks of the trade, all the black magic wizardry. And that's really what then, in a certain sense, really started to show not just promise, but started to just improve rapidly and very quickly, way beyond the state of the art.
Okay, so yeah, so that means like it kind of went back to a pure self-attention model.
Exactly.
Okay.
Exactly.
So by tricks of the trade, the black magic you mentioned, like, is this sort of like I've read that like designing neural networks is in a way more of an art than a science.
Yep.
Is that
that's
correct?
right? That's right. So basically, again, let me give you a few examples. So there are things like what was called layer normalization or layer norm at the time. This is at best heuristic way, statistically motivated in some sense, but really at best heuristic way of making sure that none of your activations go through the roof, and just in terms of their absolute magnitude, which then makes optimization incredibly challenging. And the way you implement that actually makes a difference. You can implement it a bunch of different ways. In fact, one could argue the very first transformer paper had it in a weird way, in a funky way, but it's still an effective one. But you basically need to have fast and working, verified implementations of such a trick, if you wish, if you want your architecture to really behave optimally. Another one is label smoothing, where you don't actually train your model to predict the very peaked empirical distribution of it is exactly that next word that will follow these previous words, and so basically all other words are zero probability and that word has all the probability mass. But it turns out it's easier to train these things, and you get, in a certain sense, maybe more robust parameters, more robust solutions in the end, if you smooth that distribution a little bit, and you actually reallocate some probability mass to the words that you don't actually observe, and take it away from the word that you do observe in your training data that you train your model towards. Why? We could talk about this at length, and nobody really actually knows. And so it's basically tricks like that you not only have to have, but you need to know how to use them. You need to, they're kind of these magic constants that some folks, such as Noam, for example, they just have a feel for. They've done it a million times. They know, okay, yeah, label smoothing with this kind of parameter, or here's how you apply layer norm, and here's how you implement it well. And that list of such tricks is pretty long. And so you need to have those in order for your, say, new architecture to even in a certain sense stand a chance, right? Your conceptual mechanism can be as good as it wants. It needs to be implemented super efficiently, and you need to have overall a setup in which you have these tricks of the trade at your disposal, because not all of them are going to be useful for all versions of all architectures, right? You need to start experimenting with those and playing around with it, and then you look at how your models perform and how they react to some of these tricks, and then alchemy, and then you add some others, and then you modify them a little bit, right? And that kind of tinkering, that is really this kind of art. And to drive that point home, maybe, it's now been over 6 years, and you still find in open source competitive open source code bases implementations of the transformers that use some of the same magic numbers that the original paper had, right? So there clearly is some art to this, right? And you need ultimately the art at least as much, if not more, than you need these conceptual insights of, hey, wouldn't it be more effective if we did this pairwise comparison, even though it looks kind of silly, but then iterate that only a few times in contrast to iterating over the signal purely sequentially, right?
So how did the name of the paper come to be?
To tell you the truth, I don't remember.
Okay.
So there's the story. Leon, who also joined the project actually somewhere around the time that Nikki joined, a little bit later, as far as I recall. He at some point recalls. He recalls at some point suggesting this as a relation. Well, first of all, making it clear and emphasizing that we're really going against the grain and propose a new, well, it wasn't entirely new, the mechanism at the time, right? But we had published on it before. But to take this new mechanism and really dump everything else out and just build with that, and that rapid departure from basically all other established mechanisms was something that we should emphasize and do so in a strong way, but also this nod to the Beatles. And I may not actually have been in that meeting, although I thought I was, but basically at some point he proposed that, aren't we actually saying that attention is all you need? And that stuck. But
Okay.
But yeah, again, I don't remember any of the details actually.
Okay. So it's a reference to the Beatles song.
It's also a reference to the Beatles song, but it's also it also certainly, as far as I recall, it was the way he said it at the time was probably also driven by this kind of, in a certain sense, defiant phrasing of, we don't need all that stuff, blah 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 is all you need, right? That sometimes engineers would throw around. So certainly also in part of reference to that, I would say.
Okay. So then describe the reaction to the paper, both at the time, immediately, and also in the years since.
I mean, immediately, actually, people were skeptical, and I think rightly so. So we evaluated on two tasks, dependency parsing in a very specific instance, but primarily machine translation, and really the focus was on machine translation. And if something that different is evaluated only on one major task, then I do think that actually skepticism is justified, more than justified. And so our initial reviews coming back from NeurIPS were actually kind of lukewarm, I would say. There were at least there were some lukewarm reviews among them. Somebody was excited too. But then what happened fairly quickly is that folks in a variety of different places, OpenAI is one of them, but not the only one. Sasha Rush, actually, who Hugging Face didn't exist at the time yet, but who then later joined Hugging Face, and at the time was, I believe, at Harvard? I think he was at Harvard at the time. Him, OpenAI, folks at OpenAI, Alec and Ilya Sutskever, they very quickly started playing around with this. And because they did see the promise that if this worked, then you really could have something that computationally is a much better fit for accelerator hardware of the day and of the present day too. And so as they started playing around with it, there were some initial, I remember actually having a conversation with Sasha in New York very quickly after the paper hit archive. And he had re-implemented the whole thing from scratch. And there were some issues around learning rate, schedules, and so forth, but by and large, it was working out of the box. And that was unusual because it wasn't based on an open source implementation. We did release one later, but he had done it from scratch, actually, I believe he actually even documented that project as the annotated transformer. There's a blog post that he had written up, but he was really, he got super excited, and again, others as well, by the fact that they could very quickly get something that actually trains at least as well, if not better, and an order of magnitude or more faster than LSTMs. And that, as that kind of moved through the community, it took maybe, I would say, half a year or so. So by the time we presented the paper in a poster session at NeurIPS 2017, we basically had tons and tons of interested people, and mostly still practitioners. So practitioners or somewhat more senior people who still were very, very hands-on. And then the next major event, or events, actually two of them, were the release of the GPT, before it became a series, the generative pre-trained transformer coming out of OpenAI, and BERT, which was for bidirectional encoder representations from transformers. And both of those showed that you can use these now more efficient models, training them in one way or another, either as language models in the case of GPT, or as basically infilling models in the case of BERT, that you could use those models trained unsupervised just on text. Curated at the time, it was books that they used at the time, and then they broadened it to other types of data, but that you could use these unsupervised pre-trained models to actually then either tune or adapt those models to standard tasks in language understanding very, very rapidly and just get off the charts good performance. And so that then really kicked off the next major wave of interest and excitement, especially as then both of those, in fact, actually maybe BERT in a very crisp way, they had different model sizes in even the original publication, and they showed that just making it much bigger would massively improve performance across a pretty broad range, a shockingly broad range actually, of language understanding tasks. And that then formed this, in so many ways, basically the initial spark that led to these massive infrastructure efforts that we're seeing now. It's not even culminating. There's still very, very much going on around GPT-4, Claude, and whatnot, all the very, very large models built by the Coheres, OpenAIs, and Anthropics of this world that just keep improving, actually, as we make them bigger and bigger. And that the community then grasped pretty fast. So basically around, I would say, 2019, 2020, that was in full swing. And we were seeing that these, what is called maybe somewhat misleadingly, emerging capabilities are manifesting, et cetera. And so at that stage, it kind of maybe transitioned into a mode where I was starting to get a little bit, what's the right term? I'm really looking forward to seeing new architectures that address some of the pretty obvious problems the transformer still has, and inefficiencies and issues. And so so basically now we're in a state when there was a lot of energy and a lot of effort spent on scaling these things up, applying them also increasingly to other modalities, and people getting super excited about that.
By other modalities, you mean?
All sorts of stuff. So basically, it took a while. This is maybe a slightly different question, but genomic data, images, videos, time series, all sorts of stuff like that, audio. But basically, it had at that stage now, in maybe 2020, 21, 22, become kind of the default building block. And in my opinion, maybe people, maybe the amount of effort we invested in replacing it and improving it actually started to be too little. That's gotten better this year and maybe 23, 24. but it's still not quite. I still think we really, it's about time we do away with it, or at least dramatically improve it. The multimodality aspect was very interesting because one of the other things that happened basically, I would say, around 2019, 2020, I had moved back to Berlin. We'd started working on applying, in this new group, Brain Berlin, on applying transformers to vision. There was also a group doing this here, but ultimately what we did in Berlin showed around that time, 2020, 21, that you could actually take a pretty much vanilla transformer and do image understanding with it at a level of quality that certainly rivaled and maybe superseded the CNNs of the time, and the interesting thing is, not only was it at least as good or maybe better, but it was the same architecture that you could also apply directly to language. And that, along with other such new modalities that other groups started applying this to, maybe most prominently AlphaFold 2 actually, with basically protein sequences or ultimately also protein 3D representations of proteins. That showed that now, the prior on how successful would it be if you tried to apply this architecture, or deep learning basically, to some entirely different problem, the prior just shifted. Before it was, okay, maybe we can do this. People in 2012 had done it with computer vision, with CNNs, with convolutional neural networks. Then, in 2015, seek-to-seek, and 2016, the first major launch of GNMT, the Google Neural Machine Translation System. People had then applied LSTM, seek-to-seek LSTMs to machine translation. But there were years between these major successful new applications, right? Speech recognition and so forth was also somewhere in there. But by 2020, effectively through things like the vision transformer, AlphaFold 2, etc., the community had realized now there seems to be this thing that works for everything, right? And even though that's not actually true, and even though it still does require a lot of work to make it work, people really started to be optimistic about projects like that succeeding. And so as a result, they started succeeding. And right, it's really remarkable actually. One of the biggest causes for accelerating impact of this paper was that it got people really optimistic about applying that stuff to some new problem that nobody had applied it to before, and about scale and scaling it up being one of the surefire ways of then also making it better. So that's something you can throw money at. That's something you can throw time at. And so suddenly the community went from this mode of, oh my God, there's a new thing we can do with this, to, yeah, of course it's going to work. And so we're just going to do this and this and this and this. And now we have models that can do it all together. And now we can learn from vision about language, and from language about vision. And actually the lines are starting to blur. And that's really, I think, what we need to happen, even more than it happens today with modeling video, modeling processes over time, in order to really get to the next seismic shift that deep learning will cause, which is to really have models that have a holistic grasp of our sensory experience, of our sensory environment, and are able to really get how we perceive the world, right? And that's separate to a certain extent, get ways of, or are able to perceive the world and to intervene with the world in ways that we can never, right? So on one hand, it's about really getting our reality and being able to not just generate stimuli that we generally consume, videos, audio, all this sort of stuff, and understanding our audio-visual and sensory environment, and meshing that with our conceptual understanding as captured in language, but also allowing us to suddenly learn from electron microscopy data in ways that no human could ever make any sense of, right? As is increasingly the case with things like in areas like structural biology, or design molecules in ways that we don't even understand. Not only do we not understand the rules or the mechanisms at play, we don't even understand how those design choices then have the effects that they have. But ultimately, enabling this kind of observation and discovery of aspects of our world that are completely inaccessible to us humans.
So I wanted to clarify. So
Yeah.
it seems like what's happened is that previously in deep learning, you would have specific architectures
That's right.
for specific problems, and now the transformer is like a universal architecture being applied
That's right.
to everything?
Yeah, that's right. Exactly. And that just, right, it gets people more optimistic about these new applications, but it also enables these multimodal models that cut across many applications, that bring to bear data in one modality, or modalities, bring to bear data in one modality in order to improve our understanding of another, allow us to map things from one to the other. And ultimately, right, if you think about it, language is a way for us to codify and communicate, usually only so far only between humans, a sliver of conceptual understanding of our world, right? And so one way of conceptualizing language as a phenomenon is I give you a piece of language, I give you a piece of a world, and then you can actually run that world to a certain extent, right? And that involves all the stimuli and all the modalities, if you want to look at it like that, that we can perceive, but also that we can interact with in the world. And for the first time, it's within reach to build a computer that can actually, that has any chance of getting close to our ability not only to capture a piece of a perceived world and communicate it, say in language, but also take some piece of language and then in a certain sense instantiate this kind of sliver of, if you wish, encapsulated world or so.
So are large language models just stochastic parrots, piles of statistics, or do you believe they are emergent learners that encode knowledge and understanding of the world?
Are we just stochastic parrots, or are we emergent learners? I don't know. So basically, I think these distinctions are almost meaningless, as long as we don't specifically define what we mean by intelligence, what we mean by learning, what we mean by parroting. I don't think it's a particularly useful, or many of those, if not most of those distinctions and dividing lines are particularly actionable or insightful, because we do not know how we learn. We don't know if what we call understanding is in any fundamental way truly foundationally different from just grokking the statistics, or just being a bit better at predicting certain phenomena, right? For all we know, our oh so sacred and oh so different learning abilities are just that. And if that's the case, then surely they are learning and they're learners. And so, in a certain sense, right? I'm of the opinion that I don't think there's a ghost in that machine, but I highly doubt there's one in us too. So, or whichever it is. But basically, I would, on one hand, I don't believe in the mechanistic interpretation of life, because it's not a machine that was designed but evolved, and as a result, structurally, it's very different. But on the other hand, I find it very difficult to believe any kind of duality or dualistic view that implies that there is something other than something mechanistic that makes us, that differentiates us from other machinery. And as a result, right, it could just be an experiential / data problem, right? To get them to our level of, in quotes, understanding. And no matter how you define understanding, by the way, I find it very difficult to believe that there is no understanding in these machines. It's not the same as ours. It can't be, because they're the breadth of stimuli that they're exposed to is just extremely limited, even compared to ours. But ours is also extremely limited compared to the world, right? And you see that very clearly when you look at applications of deep learning to problems such as protein structure prediction. No human, not even a field of a scientific discipline, biology, over decades, was able to produce an understanding of how protein folding happens, how protein structure emerges, that was anywhere close to being good enough to being applied in the real world. And then you come along with this black box thing and enough data and enough pre-training, and it basically just works. Now, how well it works, I think we still don't fully know, but it works certainly better than anything humans ever did by hand. That's for sure. And so it is not anymore the case that basically the breadth of data of stimuli that they perceive that the machines actually are able to tap into is just smaller than ours. It's basically just different at this stage. I would say both what we see, what we're able to learn from, and what the machines are able to learn from, both of those distributions, if you wish, are still incredibly limited when you compare it to the wealth of information that's out there.
Are LLMs a path towards artificial general intelligence?
I have no idea what artificial general intelligence is, and so I do not know. I can't, for the life of me, give you a good answer to that question.
Actually, that's a great answer. You mentioned, you think you're almost ready to move on to the next thing. So where do you think the next thing in AI is going to be?
So let's see. I mean, for me personally, the next thing in AI is actually more applications of AI, if you wish. And I think in the past and in the future, it is different applications that provide good forcing functions, or that, ultimately steer where new ideas, where we realize that the needs are unmet, and where we'll then have to improve our tools. I think if you think about basically neural network architectures, there's some obvious shortcomings of what we have today. One is the fact that you still have to take these signals, chop them into pieces, and then basically learn representations in some vector space for each of these pieces. But the problem is this chopping into pieces is something that we can do fairly well for signals that have been, in a certain sense, engineered or have evolved to have certain statistical properties, such as language. For genomic data that have not evolved, genetics, there was no reason for evolution to basically evolve genetics in such a way that license that kind of tokenization, or that chopping into pieces and then representing them. And what I mean by that is that these pieces, you can't have too many of them for our current methods. Our current methods like it when there's tens or hundreds of thousands of pieces, not more than that. They don't like it when they're too few. They also don't like it when there's still too many of these tokens, although we're getting a lot better at that. Now we can do hundreds of thousands or millions or so. But we still have constraints around those things, and the fact that we need this chopping into pieces and that we can't learn that in a data-driven manner is a massive impediment to applying these technologies effectively. Another one is that basically today, we would all agree there are some problems that are harder than others, right? For us humans. I mean, if I ask you what's 2 + 2, you don't have any issue giving me a response to that. If I ask you to, find solutions to the Schrödinger equation for some even simplistic system, way harder to do, even though we actually understand how to do it. Like, we understand the rules, but to really execute the computation, extremely difficult to do. Yet you can formulate both of those queries in roughly the same length, and the output might also even be maybe in 2 + 2 the output is also incredibly simplistic, but you can imagine situations in which the inputs and outputs have very similar shapes, and yet the compute that something like a GPT-4 or Command R or whatever would allocate in order to execute, in order to try to solve this problem, in order to give you a good answer, is the same, because the input and output sizes are roughly the same, and that just makes no sense, right? So every time a human will say, "Oh, I need some time to think about that," that's not something our models can currently do, and that's obviously broken. So right now, basically, we are making progress. There's just very recently been a few really interesting pieces of work mixtures of depths, actually an interesting one, I think, in particular. But they're still just scratching the surface when it comes to dynamic allocation of compute as a function of the difficulty of the problem, as opposed to the obvious apparent size of the input of the query and the answer that's generated. And I think actually already those two things, if we really made substantial progress on them in connection or in the context, of course, of architectures that then really support that and are efficient in that context, then we would already have made massive progress. And who knows? I mean, it seems like we're getting there, but it's these things are usually not revolutions. They look like them in hindsight, and storytelling, narrative-wise, lots of folks want to make them into kind of these singular events that somehow look like a revolution. But the reality is, as it happens, it's just a ton of hard work, building on a ton of hard work, building on a ton of hard work, and lots of people really trying their best and trying to be creative. And so when you look at it like that, then we're probably still in the beginning of really solving some of those, or addressing some of those. Taking a step back, this entire conversation, we've assumed that the hardware, and I've said this a few times, actually looks the same. And if you think about it, right, now, because this is kind of a co-evolution that's happening, right? We were joking the other day with Jensen Huang, the CEO of NVIDIA, that we were saying, well, we built the transformer to fit your GPUs. And he's like, yeah, well, we're building the GPUs to fit your transformers, and both are true. And so basically, there is this co-evolution, but it is not clear that this specific instance of co-evolution or rather, I would say it's almost guaranteed that this specific co-evolution process is in a local optimum. And meaning it is very difficult at the moment to come up with a very different model paradigm, because the existing model paradigm has been engineered already now over some period of time to fit very well to this hardware. So even though it could be a departure from transformers and God knows which ways, dumping self-attention, replacing something with something that doesn't need tokenization would all be awesome, it is actually not going to be that fundamentally different. But also, it is extremely difficult to come along and build a completely different chip, a completely different compute substrate for machine learning, deep learning, AI, because, well, all the competitive models, they're all based on and tailored to this hardware. Why would it be interesting to come up with a different chip? There is this, if you look at the history of computing, and actually, this is the perfect place to do this in the world, I would say. If you look at the history of computing, there was a switch somewhere basically leading up to the 20s and 30s of the 20th century, this switch from analog to digital computing. And right, if you look at later Lord Kelvin's Tide computers and similar super powerful analog computers that were exactly single purpose, and they had to be, almost by definition in a certain sense. What is it here? Analog precisions, some of these old analog computing devices. Their issue was that you couldn't now apply them to even closely related other problems, because these other problems would have to be addressed with sufficiently different algorithms or sufficiently different approaches that you actually had to dump out the entire computer and build it from scratch, and that's really difficult to do. And so digital computing offered the promise of being general. Right now, with in a single way, we can actually express and potentially address all computable, everything that's computable. We can actually do everything that's computable. But what's the price that we pay? The price that we pay is that we invest the majority of the energy that goes into computation into maintaining discrete states. So if you just squint at a current computer, at a digital computer today, the vast majority of energy it consumes, the vast majority of heat that comes out of it, has to go, and that energy has to be expended in order to maintain that something that actually could be a scalar between 0 and 1, actually, or more, that now it stays either at 0 or at 1. But now, with deep learning, and maybe with things like the transformer. And I'm not going to say the transformer is it. That would kind of be sad, I would think. But with something like the successor of the transformer, we seem to be in a position where actually we now have one algorithm that applies to many, many, many different relevant problems. And it's always the same algorithm. So why couldn't we now go and build an analog computer just for that one problem? And that one problem is just run a transformer, or just run the transformer's successor. Then we train such a model that can actually train new such models. We build this one analog computer for doing that, and we're done. We've basically implemented an analog computer that can be way more power efficient for something like a complete algorithm. An algorithm to learn new algorithms of the same computational shape that now are able to handle a very broad variety of problems that we really care about. Not all problems, right? Not everything. There's no completeness here, or not anytime soon. But at least that way, I think we could increase thermodynamic efficiency by orders of magnitude, not just one or two, but many orders of magnitude potentially. And so I do think that there is, taking this big step back, enormous potential for very different ways of doing all this that are building on still what we've now learned through this round of deep learning, if you wish. Anyway, yeah.
Okay. So what do you see as their greatest potential to benefit humanity and their greatest potential harm?
Superlatives are always difficult. So let's see, chatbots, you mean systems that, or some kind of, systems that have language input and output. Well, I think in general, and this may sound like a tautology, but in general, the biggest potential is that they obviate the need to formalize or to structure information in a way that is palatable to human-designed machines. You do not need to make a table in some way that is computer readable, whatever that means. You can basically just dump out the data. And if it's a table or tabular in a general way, well, maybe there's an exception. Maybe you have some place where in some row, whatever the nth field contains a note that says, that was the value, but actually I didn't really measure it that well, and take it with a grain of salt or some such. And these things that were previously, in a certain sense, from a data perspective, incomprehensible to machines, have now become totally manageable. And this doesn't hold only for data that is data, but it also holds for data that is effectively algorithms. So you can now basically have LLMs or what have you, whatever you want to call these things, that generate code, and alongside with it, human language reasoning or plans that describe what the model, in quotes, thinks this code should be doing. And now you can go and you edit the code, and your English description changes. You can edit your English description, the code changes. You can basically comment in totality on whatever was generated there. And that really marks a departure from all of these previously formulaic languages, formulaic data descriptions or data formats, if you wish, that is, in a certain sense, setting us free from the shackles of our limited, of the machines, of our previous machines' limited generality, if you wish. And I think that's, in the broadest sense, the biggest potential. The biggest harm, or again, I think, superlatives here are really tricky, but one of the maybe interesting downsides that this technology comes with, and it's I think inevitable, we just have to think about ways of mitigating this, that's maybe underemphasized, that's often underemphasized, I believe, is that we as societies, as cultures, have grown accustomed to the ability to use the difficulty of consuming, but primarily also generating text as a security tool, right? So, for example, appeals in traffic court. Why doesn't everybody file appeal? Well, because it's annoying. It's difficult. Okay, why is it difficult? Well, you need to fill out a form. Okay, that has become a push of a button. Then you need to mail it somewhere. Okay, fine, that has become a push of a button a long time ago. So how about appealing some other decision? How about affecting anything in any kind of basis democratic fashion, right? These things are rate limited by the ability of generating, or by our individual ability of generating language. But that rate limitation is gone, right? You can now generate language, even conditioned on loads and loads of information, at hundreds of tokens per second on a single GPU, right? Or faster. And so with some of these super large models. And as a result, we really need to rethink a lot of mechanisms around public services, around all sorts of white-collar crime, and it's not at all that these machines or these systems, will take initiative and anytime soon and will harm us, but they are amazing tools in the hands of malevolent actors. So I think that actually, as one of a variety, but as an often underemphasized example, I think is one of the practical dangers or downsides of this technology that we need to look into and that we need to mitigate. A lot of the times people talk about content identification or generation, identifying machine-generated content. I think that ship has sailed. A long time ago, we published a paper on watermarking contents of generative models. We will never go back to any system like that to be effective for a variety of different reasons. But I think that's also something we need to confront. There's a very simplistic alternative, or a very obvious alternative, which is we need to authenticate content, or basically certify that content was generated by a human individual. That's maybe another area, closely related area. And it's not the same problem, actually, if you think it through. But yeah, and the list goes on, but it's problems like that that we need to think about and take care of.
So how important are issues of trust to future chatbot technology?
Well, it matters, but at the end of the day, it matters in a way, and it also manifests increasingly in ways that are similar to how it manifests in humans. So we've built, as again societies and cultures, we've built lots and lots of tools that help us build trust in other individuals, and we need to build a similar suite of tools. And actually, I think they're going to look very, very similar, that allow us to establish trust in machines and systems. We have to kiss goodbye once and for all the notion that we can do this in a way that is basically by design or by construction. There will not be, as far as I'm concerned, a training objective, a neural network architecture, a data set, of whatever combination of all those things, that by construction, in an engineering manner, we can engineer to be trustworthy. Just like I can't engineer a child to be trustworthy, or a human, a person to be trustworthy. We have to educate them, certify them, recertify them on an ongoing basis, and so forth. And we have to understand better what situations are in which they might not be as trustworthy, and then just deal with that, right? I find it sometimes almost comical when there are articles about hallucinations of large language models, and they in the press it's often described as this, I should say, almost this very surprising, perplexing phenomenon. When I go to my 3-year-old and I ask her a question that she factually cannot possibly know, she is going to totally hallucinate a great answer, oftentimes, right, in a shape or form that if I didn't actually know the fact, I had no way of telling whether this was hallucination or not, as long as it's as the context of the question is close enough to something that her world model already covers well enough, right? I can ask her who the president of the U.S. is. She's going to give me, although she mostly speaks German, she's going to give me an American-sounding name, right? Maybe actually the current one she already knows, but like the last one, she's still going to give me an American sounding name. And so it's not at all surprising that these models do that. There's certainly things we can do to improve that, to mitigate some of it, but there's not going to be a correct by construction kind of a way of engineering them to be safe in any way comparable to, say, how we're trying to engineer planes to be safe, right? Even though, I guess, that also has its pitfalls, but for similar reasons. But yeah.
Thank you. So, we touched on this. You touched on this a little bit in your earlier answer, but there's a lot of discourse about both the AI might lead us to apocalypse or extinction. There's also, on the other side, utopian discourse. What do you think of these conversations?
I think there's a time and a place for everything. We should be having some of those conversations for sure. I feel the extent, the amount of energy and time and that's expended on some of them, the amount of attention that some of them get is totally blown out of proportion and often actually fanned by players very often in the industry, in the sector even, to further completely other objectives. And, say, for example, I do believe that, and this is actually an emergent phenomenon. I don't think there's necessarily any malevolence here that's happening, but I do think that it is quite convenient to, just given psychology of people in the media, of the masses, etc., it's quite convenient to be able to focus the discourse on, say, things like the risk of extinction, when you actually don't yet have an idea how to deal with some of these much more mundane problems like potential disruption or potential for disruption of civil services, public services, due to the fact that now everybody can produce like text at rapid rates or so. And so, yeah, sure, people are going to do what they learn, removes resistance or eases resistance that they might otherwise encounter, and I think that's what we're seeing to a large extent. And so, again, don't get me wrong, I think a lot of these conversations need to be had, but there are many more, potentially often more mundane and more pressing topics that I feel deserve some of that, if not most of that, airtime, attention, energy, etc. And that is a little bit unfortunate, because that's really what actually could impede progress here and could harm people on the way. And so in a certain sense, I feel we should get better at allocating resources when it comes to which of these, and this cuts both ways, but it goes both in the utopian as well as into the dystopian direction, that these extremes, right, low probability, high magnitude, sure, there are things we need to talk about, but I feel we need to spend much more energy on the high probability and much lower magnitude, but high certainty space of outcomes.
All right. What excites you most about chatbots?
Again, I think it depends a little bit on what you call chatbots. I don't think chatbots by themselves are so exciting. But I feel ultimately, especially if you include things that can interact with lots of digital systems, it really comes back to what we talked about earlier, to this generalized applicability of technology to problems in which the data and or the problem formulation / solution description algorithm are just difficult to squeeze into a traditional kind of machine suitable format. And so it's the fact that you can now deal with, say, for example, language and image content in a way that is almost algebraic, right? You can basically describe something in language, and then you can apply that function, if you wish, to another piece of language in order to, summarize a piece of text, extract certain bits and pieces of then formal information, rewrite some of it, etc., etc. Those kinds of things. I feel it's just very, and it's less about the natural way of interacting with the machine. I kind of don't care about how natural it is. I care about how fast it is and how cheap it is, in a thermodynamic sense, efficient. That we have some ways to go, but really, it's just the level of generality that you now have. It's also, yeah, it's just it offers the potential to deal with the world's information in ways that just have absolutely been impossible before.
Mm-hmm. Do we need to explore alternative approaches to AI, and why?
Alternative to what?
Alternative to LLMs.
Again, I mean, alternative to LLMs, meaning...
Or deep learning, maybe.
I mean, if you're basically thinking of things like symbolic approaches or neurosymbolic approaches, I think the answer is, in my mind, what has worked better than any other lens through which to look at whether or not something could be effective is, does it make it faster? Does it make it more thermodynamically more efficient? And if the answer to that is yes, and that's quite conceivable, right? That doing certain things in a more symbolic manner, locally sometimes, is more efficient. By all means, let's do it. But if we can't basically show that that's the case, then just for the sake of doing it differently, because we think it might be philosophically better, or mesh better with certain theoretical or certain theories of something, why? I don't know. I wouldn't understand the motivation.
Okay. And you mentioned this thermodynamic thing. So,
yeah.
What are the environmental, consequences of chatbots and LLMs, and can we make it environmentally sustainable?
So there, I think it's really important, and in general, I think this is actually, I was tempted to say this also to the last question. I think the chatbot LLM distinction is a problematic one here, because what I really believe is that deep learning overall, very large models applied to a very broad range of different problems, have the potential to drive our energy efficiency through the roof. And so when it comes, and this even just the allocation problems, but also our ability to harness energy, all sorts of sustainable energy can be optimized in some cases evidently massively. In some other cases it's going to be a little more difficult with these methods in ways that pay for the many times over, that actually it would be, to me, shocking if some years into the future, the fraction of the overall energy that is consumed by these large models hasn't gotten very large, because it is to a large extent exactly those models that will make it much easier and much more effective, actually, and much more sustainable in all sorts of different ways, actually, ultimately generate or extract, if you wish, the energy from the system.
Okay, final question.
Yeah.
Can you talk about your current venture?
Sure. So at Inceptive, what we're doing is ultimately building models, and this isn't just a AI or a dry affair. This involves an enormous amount of work, experimental work in a wet lab, both to validate methods, but also to generate training data, but ultimately to build methods or models that allow us to design molecules that once in the context of, say, your and my cells, exhibit certain pretty specific and increasingly broad functions. And so basically, I guess one way of reformulating and rephrasing that is we're designing medicines with artificial intelligence, but we're looking at a particular angle of doing this, where what we're starting with is mRNA and soon RNA molecules that actually are, in a certain sense, life complete, if you wish, right? So there's the RNA world hypothesis that everything in life can actually be traced back or started with RNA molecules. It's not clear if that's really, and we might never know how life really or where life really originated, but it's enough to know that it could have been like this, to then basically conclude that if we could only design RNA molecules optimally, which is an incredibly challenging task, we could affect all sorts of different interventions in ourselves, in these very complex organisms. Now that's definitely science fiction, but maybe we can start with a small set of functions, such as mRNA printing some protein, such as maybe detecting the presence of some small molecule or some specific macromolecule in the vicinity and expressing one protein or the other, whether or not, based on whether or not it's actually present, such as self-amplifying or self-replicating itself, which, if you wish, looks a lot like recurrence or recursion, actually. If we just have some of these simple functions, can we learn how to design RNAs that exhibit, any combination of such functions inside our cells in ways that also have, manageable or the desired consequences when it comes to innate immune responses or similar phenomena, and thus really enable medicines that are programmable to an extent that goes way beyond what we're able to do, say, certainly using small molecule medicines, but also for more mundane reasons using protein biologics, where, in contrast to those, RNA molecules are incredibly easy to manufacture. We can, in our lab, actually synthesize basically more or less any possible RNA. The same certainly cannot be said for proteins. It's much harder to do, much harder to do at scale, much harder to do, if you want to create or synthesize a broad variety of them. And so at the end of the day, basically finding or enabling one type of substrate, if you wish, in this case RNA as one family of macromolecules, that can still ultimately, when designed just right, affect the kinds of interventions that constitute, the vast majority, maybe even of all existing medicines and many medicines that we would like to exist, and enabling that using machine learning, because really, or deep learning, AI at scale, because one thing is clear, at least to us, we will never, even as, if you wish, as humanity, we will never learn conceptually how to do that ourselves. And this is ultimately because, so our only alternative is to just learn it in the sense of, or through black box methods, such as deep learning. And you can think of this just as a strict generalization of the problem of language understanding, or more precisely, generating human language, where, in human language, at least we have an existence proof of entities like you and me that are able to do it, But we've tried for decades now to understand how we do it and what the rules are that govern it, and we've failed to understand that, to conceptualize that, to build a theory around that. And instead, we've had to apply these data-driven black box mechanisms that are now actually able to do it to a pretty large extent, both understand and generate human languages. And now, in case of effectively learning life's languages, which is at least one of the at first languages, say RNA, that is the one that we want to learn first. Here we don't even have an existence proof of any kind of system or organism that is able to design these things and to comprehend how they work, and so there's even less of a hope of basically being able to design them effectively using or based on theory, based on conceptual understandings of this. And as a result, an even greater reliance on doing this with methods like AI. And we're starting in I would say, the humble beginnings on that almost certainly very long journey are that we would like to design mRNA molecules with much higher chemical stability than, say, for example, the mRNA COVID vaccines, that are actually, as a result, accessible to a far greater number of people, right? Not just, say, 2 billion people, but maybe 2-3 times that, because they don't require distribution using a deep frozen cold chain. But also mRNA molecules that have much higher and potentially carefully modulated, also over time, protein expression. Subpar protein expression or too insufficient protein expression is basically what prevents many mRNA medicines from actually being practical today, either because you would have to administer so much mRNA that you're going to get unwanted side effects or adverse effects, or because you ultimately end up only expressing or not triggering certain pathways or certain phenomena in life if the protein isn't expressed at certain minimal rates. So ultimately, you could probably enable a pretty broad range of mRNA medicines that we can't actually practically produce and manufacture today or design today, but also democratize access to them in a pretty meaningful way, and then expand the range of such properties and functions beyond protein expression and chemical stability as we go, and then eventually including things like recursion, self-amplification or replication, conditionals reacting on the environment that in those cells that these molecules end up in, et cetera, et cetera.
All right, thank you.